me.
So a couple of announcements. Any of you who have not had success with the Mondrian program, you have a few more hours to try that again. So it's till technically midnight tonight, but actually I'm only checking out tomorrow at 6 a.m. So do that. I hope it'll work for everyone. And if you have any last-minute questions, of course, on the Piazza. The other, yeah?
I just have a question. So, in case the Mondrian paper doesn't work, will you give like partial credit?
Will I give partial credit? It's hard for me to give partial credit with these things. What am I going to do? Stare at the thing and say these parentheses line up very nicely? So you're going to have to try to get something to work. Now, there is a whole bunch of things that are not that hard to get to work. Like the very simplest test cases, if you have a tiny rectangle and just have to color it, I mean, how hard is that to get that to work? And that would pass test case number 1. The next test case is if there's just one horizontal split, and then it's red on top and white on the bottom or something. And again, I don't think that's anywhere near as hard to get that test case to pass as the whole thing. So this question has come up with several people. What do I do if I just didn't get something to work? And my attitude towards this is a junior, senior level course, and I expect that students can find a pathway to maximize their score by first getting the simple things to work and then moving on to the more advanced things. So everyone should be able to get almost complete points by just passing those simple test cases, because that's how the rubric works, right? Does it pass the simple cases, and then there's a test case that says that does it pass the complicated one, and quite frankly, for the complicated one, what's the grader going to do? He's just going to look at, do those rectangles line up nicely. And does it look more like Mondrian than Picasso? And so, do what you can, but keep your eye on the fact that it does have to compile, it does have to run, it does have to do a little bit. And that's just life. If later when you work and your boss says, how's it coming along, and you say, well, nothing works, then you're not going to get a lot of partial credit for that either. So I understand when you just start out with programming, things are a little more lenient, but at this point, the expectation is that you can somehow manage your deliverables in some way. All right. The other thing is the project. So I've assigned the team. So on the same project site that had the project descriptions, I just took away the ones that didn't find takers, and so everyone here is assigned to a team. I read through the more detailed project descriptions that some of you gave. There's the team that wants to design next generation Facebook and a universal cryptocurrency miner and all of that. And my strong recommendation is to reconsider overly ambitious projects. You're going to be dealing with a programming language that in all likelihood is completely new to you, with a build system and with a set of libraries that's new to you. And so I'm perfectly fine if you take the minimum viable project that is not the same project that they have on their tutorial. So if their tutorial has a to-do list, then you should probably do the microblog, and if it has the microblog, you should do the to-do list or whatever. Do something that you want to do is something that you think is kind of fun, but keep it's not about the features of your project. This is not the software engineering class. What I want to hear later in the presentation is what was good about the programming language. Where was it a strength for this kind of application? Where was it a total pain, and why? So that's what I'm interested in. I'm interested in the programming language and its suitability to some reasonably real-world project. I'm not really interested so much in the details of, what the next generation Facebook should look like or whatever. You had a question?
You already answered.
You had a question.
So why did you not include
Oh, because in the end, almost everyone wanted it, and then I started giving out second choices, and then I had everyone assign, and I said, that's actually, it was not my most interesting thing, because it's mostly Scala, and Scala. So this way I felt everyone was kind of on an equal footing with a new language that's not Scala, and it seemed like it's the fair thing. I didn't know how these things would shake out, but as I said, I reserved the right to make these assignments, and I did. So I think this way it's fair. You all get something weird. I'm glad that I took out some of the weirdest ones that I thought people would have a harder time with, but now I think it's a level playing field.
The Emacs one.
What's that? Well, the Emacs one, I had no takers, and I'm not sorry about that, because it's, I'd much rather have you do something that you can talk about without embarrassment. But I was worried about the Seaside one, because that's an older framework, and Smalltalk is, I think, is harder for people to get into and
I heard Smalltalk was made for students to learn programming.
No. Smalltalk was actually not made for students to learn programming. Smalltalk was it's like an object-oriented version of the list machines, where you were in an environment, and at all times you were refining your own environment as you were doing what you were working for the customer. Well, it's a very interesting system, but it is difficult to get into that, and so I ended up cutting that out.
I just Googled it. It says it was designed and created in part for educational use.
Okay, can't argue with Google. Anyway, if we had infinite time, I would love to show you Smalltalk, but I don't think it's going to happen. So instead, what I'm going to show you is Prolog. And there's a good reason why I've chosen Prolog among the many languages that I could be introducing. So Prolog is this language for what's called logic programming. It's has as inputs facts and rules about some problem domain, and then one asks a query, and then it produces the answer to that query, which sounds fairly mundane. A typical application for these kind of rule-based systems, where they're used every day nowadays, are when the airlines have rules for fares. And as you know, when you want to book a flight, you go to Kayak or whatever, and then all the airlines come back with their various prices. And it used to be that there was a price for first class and economy, and that was it. And then they said, well, if you stay over a weekend, then presumably you're not a business traveler, and they give you a better price. Nowadays, for every flight, there are hundreds of fare rules. And so for the entire universe of flights, there are tens of thousands, if not more, of these rules that need to be applied to find out how much you're going to pay if you make the decision right this minute. And so those rules are expressed in one of these rule-based languages. I know a guy who used to work for American Airlines who actually used Prolog for this. I don't know if they still use Prolog today, but it wasn't that long ago. So for all I know, they still might be using this. So Prolog is, on the other hand, it's been around for a long time. It was developed in the 1970s, and so you'll see from this development environment that it shows that venerable age. But it still is in active use for all sorts of things today. What's interesting about Prolog is that, unlike when you program, say, in Scala or in Java, you don't ask yourself how the answer should be determined. You say what answer you want, and you leave it to the system, to the Prolog system, to find out how to find the answer. In that regard, you can think of it as being somewhat similar to SQL. When you issue a SQL query, you say, select this and that from the various tables with these and those properties, and you don't really worry about how the database is going to go about and visit the various tables and extract the rows and columns in which order it does that. In fact, that's one reason you pay for a database. The database has a query optimizer that knows much better than you which of the things are fastest to obtain and how to turn the query into something that can be executed quickly. So when you take a database course, the first thing that they always teach you is you should write as much as you possibly can in SQL. That it is really dumb to get the first record and then get the second record and then get the third record and look at them in your application program. You should push all of the logic into the database and let the database figure it out. And so it's the same kind of thing with a logic programming language. You want to figure out, you want the logic programming kernel to figure out as much as possible about the query execution. So it's a different model of computation than what you normally have. And a real system can often be partitioned into an imperative part that you would write in Java or Scala or C++, and a declarative part where you would use some kind of a custom declarative language. So that's the practical reason why it's interesting to look at one of these languages. But that's not the reason that I'm doing it here. The real reason is that Prolog actually is a Turing complete language. Anything that can be computed in Prolog. But it is so different from all of the languages that you and I have ever used that to program in it is kind of mind-bending, and it makes you think about programming in a very different way. And so depending on how you feel about it, you may find that interesting and amusing, or you may really hate that fact. But it gets you kind of back to how life was like in your CS1 course when you knew nothing. So if you thought that you know how to program, in a couple of weeks you will realize that that was in fact not the case. And I'm not an expert in Prolog by any means, and so I find that as well. So each time I find it kind of mind-bending how I have to think about phrasing a solution plan so that it executes well in Prolog. On the other hand, the reward is that some things that are really tedious to do in other languages are just totally dead simple in Prolog. So I'll start out with the canonical example that I think every textbook that was ever written about Prolog starts out with, namely the family tree. So here I've picked a bunch of people from medieval England who were kings and queens and their children and parents. So here they are. And I've written down these facts in the notation of Prolog. So over here I say that it is true that the male relationship holds for James 1. Yes?
So by default, is it false? If you didn't write male James 1, would James 1...
No, then Prolog would not know anything about James 1. So I'm just now writing this fact. The fact is that the maleness is true for James 1. So that's how you want to read this. And so charmingly you say, put a period after that to indicate, this is undisputably a fact. So you have a bunch of facts about these people, a bunch of facts about these people, and then here's another fact that involves two different parameters. So it is true that the parent relationship holds between James 1 and Charles 1. Now, Prolog, of course, has no idea what a parent is, or a male or a female for that matter, and so it's up to me how I interpret this relationship. I will want to mean that this means that James 1 is the dad of Charles 1. So those are the facts that I'm going to teach Prolog. The way I do that is I put them all into a file, and then I will ingest that in the Prolog system. So let me just show how to do that. So I'm going to start the Prolog interpreter. I'm going to use the command consult and load the file. You need to do that from the directory that contains the file, otherwise you can somehow change the directory or whatever. And now it's loaded in this file. And now I can issue some queries. So let me issue the query that you see here. And now it gives me a solution. It says that if X is Charles II, that's a solution. I'm going to type the semicolon key, and now it gives me another solution. It says X being Catherine also works. And I will type the semicolon again, and I get a third one, James II. And that's it. So Prolog has figured this out from the facts that I've given it. Let's have another quick look at the facts to see that it did it right. So Charles I, we can see its children were Charles II, Catherine, and James II. So it did that correctly. Notice also the uppercase X here, that's a variable. Everything in lowercase is a constant or a function. Everything with an uppercase is a variable. So I can ask it another question. I can ask it, who was the parent of Charles I? And it's going to say James I. I can say who was its parent. And apparently James I doesn't have parents. How can he have not parents?
Because we didn't decide for it.
Yeah, because in the data set there are no parents. Do you have a question?
For the previous example, where you had parent X, Charles I, what would happen if you were to press semicolon there? Would it just return false?
I'm sorry? In this example?
Yeah.
If I put a semicolon here?
No. So you query it as normal, but
Yes.
there's a James I option.
It didn't even give me that option. No. Yeah. Okay. The other thing I can ask is,
All of the parent relations.
and so now it's going to give me all of the pairs XY that are in the parent relationship. Okay?
That's interesting.
So you can see it's different from the programming languages that you're used to, that normally when you write like a function, there's a definite input and there's a definite output. But with these Prolog predicates, what's an input or what's an output is fairly fluid. So I can keep some or all of these things fixed. Yeah. In fact, I can also ask a query where both of them are fixed.
What does that even mean? Like, is James I a string? Is James I a male?
That's a very good question. So here, I'll come to that in just a second. So here I ask a question about these two fixed things, and I get a definite answer. I say this is false. Okay, so that's kind of a basic thing that you can do. Tyler asks, what is male? What is James I? They're symbols. Thanks for asking. So Prolog, of course, knows nothing about them, and they're symbols. And we'll get into that in a couple of slides a little bit more, so hold that thought. So facts are nice, but they don't get you very far. Where the real interesting part comes in is with rules. So here I have a rule that says what it means for the mother relationship to hold. So the mother relationship holds between X and Y, where X and Y are now arbitrary variables. This little thing here we can read as provided that X is a female and X is a parent of Y. Right? In that case, X is a mother of Y. And so that's how you read it in Prolog. The comma here means that it's both of those rules have to apply. So if I want to do this, I have to put that rule into my file here. It happens to be already in here, but when you get the file, it may not be. And then I would have to do the consult thing again. What the consult thing does is it compiles the file. And now I can ask mother of X. Let's see if someone who I can see is a mother of George I. And it's going to say that's Sophia. And we can see who's the mother of Sophia. And that's Elizabeth, and so on. Okay? So more about these symbols. I'm now going to have a completely different example where the symbols don't have anything to do with people. I'm instead going to do some reasoning about Java types and subtypes. So I'm going to say, it is true that person is a class. I had to write it with a lowercase p because anything that starts with an uppercase letter is a variable and not a symbol. But we'll get there. I say it is true that student extends person. So the class student extends the class person. It is true that employee extends person and that manager extends employee. These are just facts. And now I give a rule and I say, for X to be a type, X must be a class, or X must extend something else. In those cases, I will say it's a type. I just say, I say that X is a subtype of Y if one of three things happens. If either X extends Y, and that's normal object-oriented programming, right? Employee is extends person, and therefore employee is a subtype of person. Or if X extends Z, and here I've made a typo that I'll fix, and Z is a subtype of Y, because I want to be able to have any levels of extension. Right, so X is a subtype of Y if X extends subtype Z, and Z is a subtype of Y. I will fix the extends to subtype later. And finally, I say, this is Java after all, that it's true that an array of X is a subtype of an array of Y if X is a subtype of Y and X and Y are types. Okay, and now I can make a sample query and say, is it true that an array of manager is a subtype of an array of person? And Prolog will say that's true. So the right reasoning that it must have gone through is to say that an array of manager, an array of person, okay, that must be this rule here. So let's see, is it true that manager is a subtype of person? And then it would go through this logic here and see that ultimately manager was a subtype of employee and employee was a subtype of person. And it would say, yes, this is all true. So that's how it works. Now, to go back to Tyler's question, of course, Prolog has no idea what an array is, right? And so array is just a symbol. So these are all symbols. Subtype is a symbol. Manager is a symbol. Charles the First is a symbol. And so Prolog manages to just deal with these things that symbolically represent some facts and rules, and then it can fill them apart. So a little bit of jargon. So we have these different we have these symbols, and in Prolog they're called functors, just because it sounds fancier. So a functor is one of these symbols that you've seen. It has a name, and it has what's called an arity. An arity is the number of arguments. You have a unary and a binary and a ternary function, and so a function is n-ary if it takes n arguments. So if you look at array, it shouldn't be pointer, it should be array. Now over here, array is a functor with arity 1. It takes one argument. Now class here has arity 1, extends has arity 2. Manager, or Charles 1, has arity 0. Yes?
I'm still a little confused about how the subtypes are defined. Could you go over that one more time?
Okay, so over here I say what it means for X to be a subtype of Y. And I give these three rules for it. And those are the same rules that I would have normally used when I teach Java. I say X is a subtype of Y if either X directly extends Y or there is a chain of extends relationships. Remember, this one here is a typo and it should be subtype. That's one way of doing a subtype relationship. And the other way is that if if they're both array types and the underlying types have the subtype relationship. Yeah.
So I'm guessing the second rule, once you put subtype, will be like recursive?
Yes.
And then also, if for the second type definition, if you wanted to say that you need to have the second parameter also be true for class, like class of underscore must also be true, how would you say that?
I'm sorry?
So for the type parameter, let's say you only want it to be true if X extends something that is a class. So then how would you say like you want class of underscore to be true as well? Could you just say that, like class of underscore and then comma extends X?
Oh, you mean if I wanted to...
Yeah, because if you have like a male of...
Oh, yes, I could certainly say type of X means extends X, Y, comma, type of Y.
Okay.
For example.
Uh-huh.
Yeah. Yeah, so I'm not really sure that this is like the optimal way of expressing these things here. Because, I might want to say that an array is also a type, and I haven't put that in here. And so over here, now, why do I need these rules here? I need these rules because otherwise it has no way to get started. It's only going to use it's only going to be using person if I give it a reason to use person. So I had to have some way to make X to be filled in with person. So I say this is where the type comes in, because then the type gets me into these slots here. Yeah.
So if you want to go beyond just two extends, would you have to manually define that rule every time?
No, that's why I say I was just this is just a typo. It should be subtype of XY, provided that extends XZ subtype of ZY.
Okay.
Should I make that change in real time? Because and while I'm thinking of it.
Nice.
So now you see the rule that now expresses any number of. Okay, so more jargon. These uppercase things are called logical variables. That's the only variables we have, but that's what they're called. And a term is an expression that's made up from functors and logical variables. So, I guess I'm going to, again, do this in real time because I stole these slides from somewhere else. So, here I have a functor, a variable, and another functor. Notice that Sophia is a functor of RT0. Then you don't put the parentheses. So any constant is considered a function that has no parameters. So that's what's called a term. A clause has the form some kind of a term, then this provided that symbol, and then a bunch of other terms. And that's all that it is. There's no more to it. So the thing on the left is called the head of the clause for some reason. If n is greater than 0, then the whole thing is called, the whole clause is called a rule. And if n equals 0, meaning you have nothing in here, then it's called a fact. And in that case, you can drop the colon minus. Finally, a procedure is something that is a bunch of clauses where the head has the same outermost symbol. So we say this subtype is a procedure. It defines with multiple rules what a subtype is. Type is a procedure. And so the idea is if you need to implement something, then you will implement it by having some number of these rules. And finally, a logic program is a sequence of clauses plus a single term, and that's called the query. And then it's the job of Prolog to answer what that query is. So it is kind of mind-bending maybe that what you put in is just, these symbols, these functors, you combine them in some way, and then you have this automatic piece of machinery that gets some real information out of that. You can in fact write an interpreter that does this Prolog thing in a couple hundred lines of code. And so the rest of what Prolog does is just optimization and compiling and stuff. All right, so that's all we want to know to get to work with it. And I thought that this lab here is very short and people are going to breeze through this in no time, but in the previous section that was not the case. So let's take the time that's necessary to become familiar with this. So open up your Prolog interpreter. If for whatever reason you didn't install it, pair up with someone who did. And so then only one of the pair needs to do this. I really like this thing to be done with two people. It's best to have two eyes on the prize for this one. And just go through and do some of these queries. And in step 2, we're going to watch how a rule is actually developed. We want to trace through that with, there's two kinds of debuggers in the system, a command line and a graphical debugger. And try them both so that you get a bit of an intuitive feeling for what goes on here. I used to teach this the way that I would immediately teach the algorithm that Prolog uses. It takes about an hour to do that. And then I realized that if I do it right away, no one is ready for it yet. So my idea now is that, that I want you to get a bit of intuition about how Prolog works, and then we'll go into the exact algorithm in 2 lectures next Wednesday, I guess. All right, so go ahead with the lab, and in about a half hour, we'll talk about what it all means. Over this together. So I'm going to skip step 1 and step 2. The question was to define a grandparent predicate, and so X is a grandparent of Y if X is a parent of someone else I call Z, and if Z is a parent of Y. So that's how you make a rule. There were a few people who, instead of making the rule, laboriously wrote down what all the grandparents are in the same way they were writing what the parents are. But that's not really what Prolog is there for, right? It's there to let us use these rules. So here's the rule. Let's just quickly try it out. So I start Prolog, I load in my file, and now I can ask grandparent X, Catherine. And then it says James the First. And that's all it can find. So the false here means it couldn't find any more than that. I can also say, who are all the grandchildren of James the First, by putting the X here, and all the grandchildren, and then I get 4 grandchildren. I can ask, who are all the grandchildren of everyone, or the grandparent and grandchild pairs, and now I'm going to get a whole bunch of pairs. Okay, so generally is you write a rule, and then you ask Prolog to reason about that rule. Now what about the sibling? So a sibling is kind of the same thing, right? X and Y are siblings. If there is some parent Z, that's the parent of X, and that's also the parent of Y. So if I now ask the sibling of Charles II, it says, well, Charles II is his own sibling. Of course he is, right? He has the same Now you might say, that's not what you want. You don't want Charles II to be his own sibling. In that case, you would have to change the rules here. And you don't have right now a way, with what you've seen in the lecture today, of knowing how to do that, but I'll just show you. What you would now say is, you also want it to be so that X is not the same as Y, and that's how you write it in Prolog.
You could probably also define your own, like, not equal.
You could do your own non-equal, but that's really tedious, right? Because then you have to list every one. And so, in general, there's no negation in Prolog. There's no way of saying not. There sometimes is, but the details for that are cumbersome. So in general, you want to avoid not because the solver doesn't normally know what to do with it. So there are times when it can, but generally you want to be relentlessly positive about everything. So yes, having a not equal explicit rule would work, but as it turns out for variables, this rule will work fine. So if I do this, so let me consult again, and now ask for the siblings. Now you can see that it's no longer itself. Now, the more interesting thing is with these ancestors. So let me put in the ancestor rule here. Consult again, and now I could ask who are all the ancestors of Charles II. And then it says these are the ancestors. It stops here because I don't have a lot of facts in this little database here. And so what you can see is that this works nicely. An ancestor is a parent, or it's a parent of an ancestor. That's what an ancestor is. Okay? Yeah.
So it's in one line, it's an and, but in two lines, it's an or.
That's, yes, you can definitely say that like that, yes. So these, so his question was, have these two separate lines, and that is an alternative. Either one is correct, but if you have a comma here, the comma means and.
Oh, okay.
Now, what's that? Yes, so let's try the tracing. So I type trace, and now I do this query again. And so now you can see a little bit what it does. So the underscore 6066 is a variable name. So it says, I don't know what X is, so I'm going to give it some variable name. Then it says, okay, now it knows, it tries to apply the first rule. So it has Y bound for Charles II, and X is now this variable here. And now it goes to the right and says, okay, I need to establish parent of underscore 6066 and Charles II. And so now it has figured a way of doing that by taking the very first rule where it works. That's this one here. So it hasn't figured out to make any use of these two facts, but this fact here was good. So now it has bound underscore 6066 to Charles. So now it has concluded that it's true that ancestor Charles, that first Charles II is true. And in a minute it's going to give us that as the first answer. So now it keeps on trucking the same way that it had before. So the redo says that it didn't think that this line of reasoning was exhausted. So it tries it again. Now it makes a different step, so let's see what it's trying to do now. So previously, you've seen that it's at 6066 and Charles II. It no longer does that because it says, look, I've tried this one here, and I'm done. So now it's going to go to the second part here. So it's now going to establish parent of X, comma, Z. Okay, you can see the two variables in here. Now it has found a solution to that. And let's see which one it took. It took the very first one, and that matched this pattern, so it's good with that. Now it calls, now we're here, so now it tries to do this part here. So you can see that because Y was Charles I from the outset, that was always true for our query, and now it has found something for Z, namely Charles I. So now it's going to try to prove that Charles I is an ancestor of Charles II. And so now it's going to try the first rule again, see is the parent relationship true? I don't remember, is it true? Yes, so it'll succeed with that. It'll succeed with that, it'll succeed with that, and now it has an answer. And so in that way, it goes through this thing. So let me go to the more interesting case. What happens if we make a subtle change to this? So what I'm going to do is, I'm going to change the order here and put the ancestor first. And now if you think about it, that should still have the same logical meaning, right? Because now I say X is an ancestor of Y if Z is an ancestor of Y and X is the parent of that Z. The same thing, in which order I say it doesn't logically make any difference, but as you'll see, it does make a difference to Prolog. So in that regard, Prolog is not like a purely logical thing. It is an execution engine, and we have to get a bit of an understanding of how it works. So let me save this here and reload this. First of all, I'm going to turn the tracing on. How do you turn tracing off?
No debug.
Yes, so you have to say no debug. Notice the charming inconsistency. So now if I ask for all the ancestors here, I'm going to get Charles I, I'm going to James I, and then I'm going to get a Stack Overflow. So obviously it made a difference. Now to debug that, I can do it the same way, but there are two recommendations that I have if you have that situation. First of all, try to pare down your data set. So I'll make it so that we're having here Charles II. I'm going to eliminate all of these guys here. Oh, okay, I'll take this guy so I have a little bit to work with. So I'll consult again. And so, and now I'm going to use the GUI tracer and to trace. So here's the GUI tracer right from the 70s. And I have not found a way to change the font size, so clearly pixel resolutions were not what they are today when this thing was written. And so here you can, if you hover over, you can see this thing says step. And so when you click on here, you can kind of see what it's doing. And you can see where it picks the parent. And now it's stopped here, so this thing is grayed out because I need to hit the semicolon thing over here. Then I'm back in here. And you can see here the call stack of what it's trying to achieve. And so at this point here, it's found the second answer. Now I'm going to click my way through here, and you can kind of see what's happening. You can see that the call stack gets higher and higher because it keeps trying to find, it keeps trying to use this rule. So the first rule gave it no happiness, and then it goes to the second rule where it now tries to prove ancestor of zy, where it keeps creating new and new variables, and it can never satisfy that because the first rule just, it's run out of solutions, and that's where the infinite recursion comes from. So this will undoubtedly happen to you in the first homework, where you're going to have similar situations and you're going to put them in the wrong order, and then that means you need to look at the ordering of the rules and see if changing that makes some sense. The general way that you want to do this is that you always want to achieve some kind of progress early on. It's easy for Prolog to figure out parent XZ. That simply means to go through all of the parent computations. And so that's the thing that you want to do further, because that way you move the computation to something where then it makes more sense to do the recursion. So you're going to get that kind of intuition over time. This debugger is, if you need to do this full-time, it's worth learning. As it is, I think you know enough to play with it if you want to get some amount of intuition. And it'll make somewhat more sense after next Wednesday when we talk about exactly what Prolog does. All right, so I hope that gives you an intuitive idea what this thing does. We'll have two homeworks with this. One to just give you basic Prolog practice, and one we're going to be putting this to some semi-awesome use where it's going to predict where it's going to solve some puzzles for you that would be hard to solve without it. All right, so if you haven't done so, turn in your homework for the Mondrian thing and get started on the project. Well, someone said, should you get started on the project? And I would say absolutely yes. Put in a couple hours, install what needs to be installed, do the first demos, become familiar with that unfamiliar programming language, and then write up in the progress report, log in a couple of hours with what you did. So this week is definitely when you want to get started. If I get empty progress reports, I will send out reminder messages. Thank you.